Hey everyone, welcome to another episode of Eigenbros.
What's up, guys?
So today we're doing an interesting topic. It's about the, how would you say?
It's on the mathematics of physics.
Gotcha. Yeah. So we kind of go through, I guess, we follow the timeline of history a little bit to see how things build on each other and the mathematics that was required to do certain physics, and maybe even why we use certain math for physics.
Yeah.
Right?
So we kind of go. We go in history order, like Juan said, but we talk about some conceptual things, even have some more metaphysical questions in there every now and then about math.
Yeah.
So it's an interesting one.
Yeah. So hopefully this topic is interesting to you, and if you have any questions, just leave them in the comments for us, and we hope you enjoy it. And
make sure you guys, once again, just subscribe to our channel, like, comment, share. And then also follow us at Twitter at Eigenbros, and then go to the website, eigenbros.com, to see all the podcasts, the YouTube podcasts up there. And we also have TikTok, so follow us on there. And am I missing anything else, Juan? Do you know?
No, I think that's it.
All right, we'll see you guys in a bit.
Yep. Okay. 3, 2, 1. Bam, 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 bam. I went slower on
Solid.
that one.
Yeah, it was a little solid, slow countdown
Morose, there. We're at this level right now. Welcome to another episode of Eigenbros. And we actually are doing a requested topic today, right?
Is it?
I think somebody in the comments said, we want to hear more about this topic, this point of contention between you and I.
Let's just give a little recap. So we were debating at one point about, does math need to be beautiful? And I don't know if it was requested per se, but definitely people latched onto that. It was during our, what was the podcast? Was it during the aliens one?
No. Before that. It had to do with the history of energy or just energy, I think.
Okay. Yeah, it was one of those. And then people kind of took to that one. Yeah. So it seemed like it was of interest.
They were like, okay, well, let's expand on this.
Yeah.
So this kind of motivated. This is going to motivate our discussion today. And maybe I guess Terrence's formal way of summarizing this. How would you put it?
Well, I guess basically what I wanted to do today is just kind of talk about the mathematics related to physics, and we can kind of go all around. And I want to keep it, in the realm of like intuitive, the philosophy behind it, that kind of thing, but not so much in the details of like, you need to multiply the eyes, the imaginary parts, and just keep it kind of good for laymen, enjoyable for laymen, and enjoyable for physicists as well. Yeah,
and I know, shout out to one of our fans. I recently saw that one of our fans is 19.
Oh, yeah.
Yeah. I forget I honestly am bad with usernames.
Okay, this is the one from the video with the Feynman Me Too thing.
But shout out to him or her. I don't know. I don't know their gender, but shout out to them. Thank you for listening. And it was even for you, like you're starting out probably your physics career. We do content like this so that, a lot of you can get kind of a bigger picture of what's required in a lot of ways. I think we have a fraction of our listeners that are in that group.
Yeah, for sure.
So, but for those of you that are just sort of interested in physics in general, this is one of those episodes where we kind of dive into the machinations.
Yeah.
Right? Yeah. So where do you want to start, man? There's so many places that we can kind of go to. I mean, we can go as far back as, Greek antiquity.
Sure.
To Pythagoras and Archimedes and stuff.
Absolutely. Let's do it. So, of course, with the whole advent of mathematics, it seemed like it kind of stemmed all at the beginning from geometry. Yeah. So, and that kind of makes sense, right? Because it's this very Newtonian sensibility where we have kind of of course, this is preceding Newton. Yeah. It's preceding Newton, but
we'll explain further on this one.
Yeah. So the way I'm thinking about it is Newtonian in the sense that humans reside in the Newtonian world. The classical world is what we're familiar with. So we like spatial things. We like shapes. We like movements like velocities and things like that.
What we typically mean in physics, when you hear this phrase, if you've read some physics books casually, you'll see people mention the Newtonian regime, which is like Terence is saying, it's in the length scales where we can make sense of things.
Right.
Like not too big, not like planetary scales, or not like quantum scales where things are really tiny.
Mm-hmm.
And also time scales that make sense, meaning non-relativistic.
Right, and relativistic meaning like when things travel at the speed of light, then space-time is connected in a way that's not...
not trivial, not doesn't make sense, not intuitive.
Well, they're coupled now.
Yeah.
Where you can't just analyze time and space independently like we can in our normal frame of looking at things.
Yeah.
You actually have to consider both of them at the same time.
Yes.
So geometry is one of these things that resides in a very intuitive Newtonian intuition. So that's kind of how mathematics started out, with guys like Euclid and then guys like Pythagoras, as you mentioned.
And it's sort of... It makes sense, right? Because geometry is static. There's very, it's not going to change. It's something that doesn't evolve in time or anything.
Yeah.
It makes sense that we would start there as a building block.
Right. Yeah. It makes a lot of intuitive sense. Mm-hmm. I think this is also why I'm so attracted to geometry too. Mm-hmm. From when we used to do homework all the time, and everything, I would always try to put it in a visual or geometric framework.
Yeah.
And I think a lot of times some physicists don't really like geometry because, we found the power so much of algebra or, algebraic equations that you can ignore geometry a lot of times. But I've found that the most enlightening and illuminating things are geometric and have some kind of spatial or dimensional quality to it that you can visualize. So, I really like geometry a lot. And this is kind of how mathematics began, which makes sense.
Yeah,
it's very intuitive.
Yeah, to be fair though, let's give So algebra, by the way, I think was invented before geometry.
Was it really? I thought it was invented afterwards.
I think
maybe I'm wrong.
So algebra is Arabic in nature, and they developed algebra. I think might have been developed in Egypt. There might be some historical contention there. I think it's in Egypt as far back as then, which I believe precedes the Greeks for sure.
Their culture does, but they also existed.
But they also had sacred geometry too, which is But I will say that the Greeks kind of refined it in a manner that was axiomatic and stuff like. I believe. Okay. It could be that they transcribed these algebraic. It's escaping what I just said.
What? The algebra?
Wow, I'm blanking on that total brain fart.
Well, we can circle it back if you remember.
No. The Egyptians at the time or whatever, they might have the Greeks just might have, transcribed their knowledge of geometry and refined it in a manner that now it's sort of westernized.
Right. And we know that the Greeks have done this a lot of times. They'll take different parts of different cultures and then improve and expand upon them. So I could definitely see that.
So they may have synthesized it in a way that pushed the boundaries on that further.
Right.
So just so you know, this they're not necessarily the start of all this. They're the people that are probably most prominent because they left a good record behind.
Right. And they also pushed it to limits that, may not have been pushed in other cultures at the time.
Yeah.
So, geometry, algebra, those are the beginnings of mathematics.
Yes.
And those coupled are extremely powerful, right?
Yeah.
And we use it in physics all the time. You pretty much need algebra and geometry at least to start doing, any kind of Newtonian classical physics.
Right. The
basic level.
The funny thing is algebra was actually developed to help. I remember reading this in a book a long time ago. I don't know if there might be a grain of truth to this, but it was developed so that farmers could could assess the acreage that they had and the value of their acreage.
Oh,
funny enough,
that sounds geometric too.
Yeah, so they had to use some geometry, and I mean, geometry wasn't necessarily like basic geometry wasn't foreign to the Egyptians, right? They built the pyramids.
Yeah,
I mean
for Christ's sake.
Yeah, they had this sort of sacred geometry point of view, and I'm sure the Greeks kind of took this to another level, you know. But at least the first sort of physical, natural, what did they call it? What did the Greeks call it? Natural philosophy, or So,
but you're talking about like not the actual like philosophical thinking stuff. It's mostly like the attachment of like numbers and things, and the science to things.
So the Greeks actually, the first example that we're taught is Archimedes' principle. And this is like the name that comes up to explain what Archimedes observed when you submerge objects into water.
Right.
And
do you remember the story behind that?
No. Do you?
So I think I do. There was something with a king, right? And I don't remember the details, but the king had some suspicion that the crown was not real. And I don't remember why he even thought the crown wasn't real. Maybe he got it from someone else or something. But there was a suspicion that the crown was not actually gold. But they had no way to prove it or tell at the time. So Archimedes, being, you know, this really well-known, high, prominent, smart guy, you know, hey, he's a smart guy in the group.
You figure it out.
Yeah. So they say, okay, smart guy, you figure this shit out and tell us a way to make this so we can figure out if this is gold or not.
Yeah.
So Archimedes, you know, he sat contemplating on it. And then one day he was taking a bath or something. And then he has the whole eureka moment where he realizes that density is this quantity that doesn't change when you have the mass and the volume combined. So mass divided by volume is density. And he was able to figure out that a density of gold is different than the density of, let's say, like silver or copper or something. So when he put the crown submerged into the water, it had a different density than it should have had if it was actually gold. So that's how he was able to figure out that the crown was fake.
Yeah. Because the two materials have different densities, and so the displacement of the water will be different.
Right.
So and that's actually the first sort of physical thing that I remember being taught.
Okay,
like in a sense, the Greeks had, oh yes, this is interesting, and also they had sort of unrefined ideas about certain things, like
right.
Like
it's like little life hacks almost. It's like a little toolbox of life hacks they discovered.
Yeah, like they discovered, well, one guy, I forget his name, but you know, he thought of things, he thought things were built from, you know, in what did he call them? Like the atoms. Like he had the idea of atoms, but he called them,
they were called like inseparable or indivisibles or something.
Indivisible, indivisible. Some indivisible thing. He was like, the world is made up of these indivisible particles that we'll call atoms, basically.
This was like what was it, Democritus or something?
I believe so. But this is what I'm saying, though. All these ideas kind of came, and these guys kind of thought really hard about these things before they could even really have the mathematical tools to describe what was going on.
And it's actually interesting how some of them might have even had a thinking that is logically not really all correct, you know, because of nowadays we have such good proofs and we have such good rigor that some of these ideas were not really they did not pass the test of complete logical airtightness. Like the whole indivisible thing is like, it can be, but like, how do you prove that that's the case, right?
Well, this is the scientific method.
Right. But those assumptions, a lot of those times, carried us out to such a level that those assumptions were actually really good at the time because they were able to take us at such a far way. Like this is kind of when we look at the energy podcast, the one that we did about what is energy, how Descartes came up with the idea that there should be some conserved quantity in the universe of motion. You know, the vis viva controversy, that whole thing. This was like this was a metaphysical, philosophical idea that actually carried our physics and our science to such a level that without that idea, I mean, I think it wouldn't have, I don't know if we would have gotten as far. At least maybe somebody else would have created it, but that idea had such a power to it that even though it was flawed and not logically
correct nowadays,
it still took us into a realm that was actually very fruitful, it seems.
Yeah.
Scientifically.
Yeah. No, 100%. So that's kind of where we begin our journey a little bit. Then we move a little bit forward in time, and we end up with Newton.
Okay.
Newton was the next guy up.
Right.
There's a lot of people in between. I think optics, to some level, had been developed.
Yeah, we got like Galileo.
Yeah.
Who else? Copernicus.
Yeah, because a lot of these Greek antiquity guys were kind of fascinated by the planets and planetary motion. So we had developed already a sense of, well, math not only that was there, like, okay, angles. They were actually able to accurately measure to a small error bar the circumference of the Earth.
Yeah.
Just by using lengths and basic geometry.
Right. And that's a really cool one, actually.
That's
you know that
amazing.
one?
Yeah, but it's so awesome. Like, you're always like, how the fuck did these guys figure out, like, the radius of an Earth in, like, BC?
It's insane. But you have to know. So it's funny. I was given this problem on a test before I knew about how they did it.
Okay.
This was like, it blew my mind because.
And they asked you to come up with your own way?
Yeah.
Oh, that's cool.
This was before I knew how to actually do it, but it blew my mind because I was like, how could you figure it out?
Yeah.
But it was like using basic geometry and the height of certain things, like figure out the radius of the Earth.
Right.
And anyway, I think I got it. I think I did it right. I don't know. But basically, do you know the story of how they did it?
Yeah. It was the whole, okay, so it was, damn, who was the guy though?
Ooh,
do you remember?
Sorry, I don't remember your name.
I literally just made a post. Well, not just, but I made a post about this on Twitter at one point. Damn, I wish I remember the guy though.
Well, your work isn't, it wasn't done in vain, Mr. Mysterious
Unknown man.
Mr. Smart Guy, Smarty Pants.
But yeah, there was a thing where he had a what do you call it, a courier or something, walk the distance from one known location on Earth to another known location, and the guy tracking his number of steps.
Yes,
right, and he actually said, okay, he made a mental model on himself. He said, okay, I'm going to make the assumption that the Earth is actually a circle or a sphere.
Yes, and
then he said, okay, I know that if that's the case, then if light is hitting this particular building that's X amount feet tall, the shadows should be in a certain way at this time. So at one location in time, let's say I'm going to make up a random location in Egypt, in Cairo, Egypt.
The shadows should be the same.
The shadows should be this way. But then in the other location, B, if it's far away enough, let's say if the Earth was flat, the shadows would always be in the same direction. He noticed that the shadows were not in the same direction at the same time. They were at different angles. So then he used that information to actually be able to see that
the arc radius,
the arc length, of that travel distance. Yes. We know a formula that relates arc length with radius and angle. So just with that information alone, he was able to calculate the radius of the Earth, which is fucking mind blowing. So
it's like, what?
Yeah.
Man, that's something.
Yeah,
man.
that's one of those things that's just like, damn, you realize the power of just simple geometry and mathematics right there. It's just like, you always wonder these things. When I was a kid, I was like, how is it possible that people know the mass of Earth?
Yeah.
Like, there's no giant scale. Like, how do you know?
Yeah.
But it's all of this physics that, you don't realize how linked up everything is until you start studying it. And then you're like, oh, the physics and mechanics of the universe are all consistent in such a way that's really beautiful.
Yeah.
And mathematically, everything correlates really well.
Yeah. So, I mean, these guys a lot of these people were doing experiments from then till Newton, but Newton is the biggest figurehead for physics.
Yeah. He's the father of physics, we call him, I think.
Yeah. The father of modern physics. Because a lot of this, right, sort of in a way, like
I don't know what would be as opposed to the older physics.
Antiquity, yeah, because like the Greek guys were like the physicists.
Okay, you can divide it in a couple eras.
Yeah,
okay.
yeah. So that would be like those between the Greeks and Newton. Like that defined an era of like people that were.
Well, I would kind of think
optics.
of fathers of modern physics, like the people who
started the advent of quantum mechanics.
Right. In that sense, yes. But I'm saying like if you were to separate there's a clear delineation between calculus and geometry and algebra. We were just functioning off of. So there was a point where new mathematics had to be developed because we started reaching limitations.
Right.
Yeah. And
true. Okay.
Yeah, you know what I'm saying?
Yeah, and the calculus is kind of calculus is still relevant today.
Yes.
And actually, that kind of leads me to an interesting question, Juan. So let's kind of divert on the history lesson a little bit.
Okay.
And let's do a little bit of conceptual thinking. So, or I guess philosophical musings. What do you think, man? Do you think that we'll ever come up with another mathematics like as strong as calculus in the future for a new kind of physics?
Well, the thing that makes calculus useful is that it's analytical.
Yeah.
And I don't know.
But will we like graduate to a new regime of math that's just like
higher analytics?
Maybe not even necessarily analytic, but like, will there be some new regime of math that's just like, that is the new kind of calculus for this particular type of physics? I know this is like
need to
such a metaphysical question,
you're
but
right.
what do you think?
No, I think you're right. I mean, there's constant. There are these things in physics. Well, it's kind of funny, but there are things in physics that do require development of new mathematics, but necessarily it functions in the sort of what physicists call differentiable space.
Okay.
I mean, you know what I'm saying? Like,
yeah.
It's not.
It's still within calculus. Umbrella in a sense.
Yeah, but these are all tools. Like we build different sort of mathematical models that we work in, but nonetheless, we try to bring it back to calculus because that's what we know.
Right.
So in a way, there's nothing that says that we can't develop a new form of math.
Right, because we're always developing new forms of math, right?
Yeah, new representations and stuff like that. And it's all symbolic. Like if you could build new rules and new things that could help you kind of solve problems, it's this is the powerful thing. It's just a higher symbolic set of rules that allow you to do a lot of things. That it's very powerful.
Right. They've all followed very logically, it seems. But I'm wondering, is there going to be some new game changer in the future?
And we might reach a limitation with calculus if things don't really, nothing new happens for a while. We may start to be like, we need to reassess how we can characterize things because maybe calculus isn't doing it.
Right. I'm hoping that we are going to be at that level because I feel like we're already kind of hitting a crossroads in physics. People talk about how like there's no new physics really.
Math breaks down, that kind of talk.
Yeah, exactly. Yeah. The math breaks down. We need to use renormalization for, let's say, like Q of T and everything. Yeah. Like Dirac didn't like renormalization. He thought it was a shortcut and kind of a sloppy way of covering up what should really happen.
Those may be glaring signs that calculus may not be the only math we need.
Right. Maybe there's something beyond our reach. Like my fantasy. This is kind of like don't think this is like means anything really, but I'm hoping that something crazy will happen, like when someone solves like the Riemann zeta function, like something like that. I'm hoping will produce some kind of new architecture or something along those lines where we discover some kind of new mathematics that's extremely powerful. Yeah,
man. It's definitely possible. And I think we may reach a point where enough people say, all right, enough is enough. We need to go back to the drawing board. And I'm sure there are a bunch of mathematicians already understand this, more than likely.
What's that?
They understand that we take calculus for granted in a sense. I think they intrinsically understand that maybe that they need to develop new math but they're just kids in a sandbox. They'll make different castles and stuff in different buildings. So a lot of the time we leave this up to the mathematicians out there. If you're a mathematician, see if you can develop a new kind of analytical.
Good luck.
And something to revolutionize.
See you in 50 years.
Revolutionize a whole new field that that takes a lot of.
Yeah, because you need to know all the stuff before it to get there too.
Yeah, because I mean, like I said, we reached limitations with algebra. Algebra's clear limitation was, I mean, here's the thing. The idea of calculus isn't necessarily entirely foreign, because by the time Newton was around, there was a thing like Riemann sums.
Yeah.
There were things like calculating slope.
Riemann was after Newton.
Riemann was after Newton.
Yeah.
But how would you call summations? Let's just say Let's just say summations weren't new.
Yeah, so the whole part that kind of makes calculus next level was the whole idea of the limit.
Yes.
The concept of the limit, because the limit then allowed the differential to exist.
Exactly.
And that was the whole big moment there.
Yeah.
Because, I mean, a derivative is literally just like a slope.
A big slope, yeah.
Yeah, it's just a tiny, or it's just a slope that approaches an infinitesimal value.
It converges to a point. The number is small enough. The difference is small enough. So if you guys, recall back to slope.
Yeah.
Change in y over change in x.
Right.
Right. All the calculus says is that we take the change in y and the change in x.
Yeah.
And make that change really small.
Yeah.
Really
where
small.
Where it's so small it approaches like zero.
Yeah. And that's the game changer of calculus. Basically your that starts to look like a point.
Right.
Yeah.
Right.
And that's the genius of Newton.
Yeah.
He was like, it starts to look like a point, and at that point it's a tangent. You could treat it like a tangent.
A tangent line to that point. Yeah. So that's the whole game changing part of calculus. Is the limit. That's the meat of it, I would say.
Yeah.
And you can extrapolate everything from there, the integration and all that stuff.
And that's
derivatives.
But he needed that. He apparently Newton had developed calculus out of necessity because he was trying to do certain experiments that required this. I think he was trying to solve this momentum kind of conservation issue.
Oh, was that it?
I think he was. He was doing experiments where he was like he was trying to solve forces, and forces didn't make sense. And he was trying to make sense of it all, and acceleration and all that stuff. And, and that's where you get F equals ma.
Right.
You get F equals m times the derivative of the velocity over the change in time, pretty much.
Okay, yeah.
Or the derivative, change in velocity over change in time.
No, you're right. Yeah.
So yeah, it's man, it's just
it's interesting.
It's fascinating, but yeah, this is all. It pretty much starts with Newton. Modern physics starts with Newton because we say modern because the calculus.
All right.
And that's necessary. You know what I'm saying?
Yeah, I get you.
Like all of modern physics is based on calculus.
Yeah.
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 Pretty much.
Yeah. So that's why he's sort of the founding father in a way. And then the guy Leibniz, he's also
Leibniz.
Leibniz is also in the picture. I think actually I have a question for you. Do you know if integral calculus, so they also say like integrals are the antiderivative, if you've heard about integrals.
Yeah, so derivative, what we were discussing is basically the operation of the slope.
Yes.
And then if you want to undo that, you take an integral.
Yeah.
But the integral is actually also more powerful than that because it has crazy properties where you actually get the area too. But,
I think the integral is a lot more fun to do.
Yeah, of course. Everybody, you hate the integral at first when you're learning calculus because you're like, why is it so damn hard? But then you learn to respect the integral massively the more you go on.
Yeah. Honestly, if you're taking calculus 2 is probably the hardest out of all the calculus.
Yeah.
Because you deal with integrals. This is the one semester where you spent on integrals entirely.
Right.
And it's rough because there's so many integration techniques.
Yeah, yeah.
And I think it's a lot more powerful than calculus because Calc 1, which is derivatives.
Yeah.
I think it's a lot more powerful than derivatives because a lot of the time you're looking for a solution. Not necessarily because with derivatives, you have a solution.
Right.
But you're just taking an operation.
Right.
Yeah. So in a lot of ways, if you're a physicist, you'll probably be doing a lot more integrals than derivatives. For sure.
And of course, some really good channels to plug for integration. I'll just say is black pen, red pen, and also flammable maths.
Shout out
just
to
to fit them in there.
Yeah, check them out if you need some hints or pointers on.
I always love looking at those integrals that they come up with and see. It's fun.
Yeah, no, but that's why integrals are more powerful
Yeah.
In a lot of ways. And yeah, it's and the history and development of calculus, it wasn't, let me just say this too. It was not perfected when Newton was around. When Newton was around, he had just introduced the idea of like taking limits and stuff.
Yeah. But it was kind of nice that he came out at the same time as Leibniz, because then them combined actually did like have a really nice picture of calculus. Yeah, because Leibniz came up with things that Newton didn't see, and arguably Leibniz had the better version actually in some ways.
Yeah, in some ways, yes,
because he had this really powerful notation that Newton didn't have.
Yeah,
but I'm sure Newton also had some things that Leibniz didn't think of, but I don't really know off the top. I just, because we have adopted the Leibniz notation because it's so fruitful. It treats the derivatives like they're fractions, although, of course, any mathematician will shoot you if you ever say that a derivative is a fraction or a quotient. It's actually the limit of a quotient. But, yeah, we won't go into that.
Ooh, they hate us for that.
Yeah.
They do.
Physicists treat it like a quotient all day long. We don't give a damn.
It's awful. It's awful because I was, when you're being taught by mathematicians, by the way, they will say the same thing. And, in fact, they teach physics classes, so I always felt uncomfortable doing substitutions, because we treat it like a quotient.
Oh, yeah.
Yeah. So,
dude, it took me so long to even understand, because teacher would say it's not a quotient in math class, so I would always have hangups about whether I should treat it like a quotient or not.
Doing substitutions, right?
Yeah, but then I realized that I can always treat this like it's a quotient. Like in physics, being a physicist, I've never run into a problem where I've not been able to treat it like a quotient.
Yeah.
Of course, I'm sure that will bite me in the ass at some point. But I'm just saying, you could get through a whole like graduate career. Well, of course, at least half a graduate career, and never have to care about not treating it like a quotient.
Yeah.
I've never had a problem.
Yeah. No, it's only when you talk to mathematicians. But
yeah.
But yeah, you'll more than likely run into this calculus, right? You run into calculus, and honestly, calculus is not, if you're interested in physics. I have a friend who's Ricky. Ricky's interested in physics, but he's a little shy about the math, and I tell him calculus is not that difficult. And I say that
mathematics in general, I would say, is not that difficult.
It's not as difficult as it seems. It's daunting. Yeah. That's all it is. It's like, it's
especially when they start to get in that alien language territory with abstract algebra and shit.
Yeah, no, when mathematicians get, it's because they're mathematicians writing this, and they're writing it for other mathmaticians a lot of the time, or people that are interested.
I think the hard part of math is probably the proofs.
Yes,
because proofs are now requiring you to do some thinking. The easy thing about math is it's a formula usually. Like, math is a toolbox, right? I've always liked math because it's basically like saying, okay, here are your tools. Here's your wrench. Here's your screwdriver, and here's your hammer. This is how you use
it to fix your problem.
Yeah. So there's never any ambiguity in how you go through the steps. You just fucking hammer the nail if you see it.
Yeah.
You screw the screw if you see it.
Yeah.
And there it is, right? Yeah. The hard thing, I've always found physics to be harder because physics says, like, now you've got to say, okay, I have my tools. How do I actually make this
heavily
like if you're going to build a let's say, for like a carpentry example again, if you're going to build a bird house, you're going to say, okay, I have all the tools. How do I actually construct this birdhouse? I need to like measure it. I need to design it. I need to do all this.
Yeah.
That's kind of where physics is at. You need to actually use those tools.
Yeah.
So you have to do thinking actually, but then math, you have to think when you're doing like proofs.
Yes.
So it just depends on how high up you go. If you use math as just a tool, then it's easy. But if you're using math to like actually prove things like that, that's a little bit harder.
Yeah, it's So shout out to all my math buddies. Yeah, and it's anyway. I kind of wanted to keep going on the physics thing. Like, you'll get into more calculus as you go along, and we start getting into electricity and magnetism. So after Newton's era was defining the three Newton's laws. Equal and opposite reaction, an object in equilibrium will stay in equilibrium.
Inertia.
And then
F equals ma.
Yeah. The sum of forces. So it's a simple principle that was powerful for a good amount of time until it was exhausted.
Yeah.
And then you get...
But damn, it was powerful for a long time.
Yeah, it was very useful.
That shit yielded a lot of good stuff.
Yeah, and by the way, that was in the regime of forces. So there are a lot of different analytical routes you can take. With forces came the notion of vectors, because someone pointed out that, well, forces have, a certain value and a direction as well.
Yeah.
So you have to take that into consideration. And so...
Do you know who created a vector?
No.
I don't either. I was just wondering.
All right. We'll leave that up to you.
Rick
Do you know?
Vector.
Yeah, my name's Rick Vector. It's some guy from America. I don't know. But anyway, this worked for some time, and then little by little, there was these guys that were like saying, well, this is not sufficient. There are probably better ways to solve problems. And and they're like, well, energy. Here's a thing that is conserved.
Mm-hmm.
So,
of course, don't make it sound that easy, Juan, because we did a whole video on what is energy, and
it
ain't that cut dry.
It's not that cut dry.
This is like hundreds of years in the making.
Yes, it is, and you should go check that out.
Yeah, it's a really messy process.
But in summary, there were these guys like Hamilton, right? I forget his first name. Hamiltonian.
Oh, yeah. Hamilton, yeah.
Hamilton and Lagrange.
Okay.
So these two dudes
you're going right to the fanciness.
Yeah.
Okay.
Well, they had to refine it. There were these guys that were thinking more clear. They wanted a more universal approach to solving problems.
Right. So they went up several layers of abstraction to kind of achieve that.
No, but you needed physics for that.
You do, but they're like... They took that physics and then made it more of a generalized version, or they abstracted it away now. Yeah. And of course, when you start abstracting things away, you get really nice and neat. And a lot of these, I've noticed that I think that's the whole point of abstraction, right? Mm-hmm. When you take things to a higher level of abstraction, you usually can hammer things down in a simpler way. Mm-hmm. Like, it seems more daunting and whatnot because you're detaching these things from kind of a physical concept.
Yeah.
But then when you abstract them away, you're actually making it so that it's easier to hold a bunch of stuff at once.
Yes.
Once you get past that threshold of what the fuck is going on here.
Yeah.
And that's kind of where Lagrange and Hamilton were taking the energy concept.
Yeah. So they were still in the regime of calculus, obviously, right? But they had noticed that you could take, and you can watch this. I'm pretty sure this was when Emma Noether. Noether. She had already developed this idea that energy is what physicists like to say is invariant across translationally. So invariant in space and in time, if it's conserved. If it's meaning if there isn't something that's leaking the energy out of the system. So the energy is constant, right? So these guys were like, okay, this is a very important property, energy, that doesn't change. So we can definitely use that to our advantage, and we can construct a whole mathematical, how would you say, formalism or toolbox to help us solve physical problems. We could look at things just purely in terms of energy.
Right.
And that idea was so powerful and revolutionary that we still use it today in modern physics over everything, because you don't have to deal with any nasty vector stuff.
Right.
You don't have to deal with, like Newton's algebra was still, Newton's calculus was still using a lot of like sort of basic algebraic kind of, like, how would you say? It wasn't that complicated.
Yeah. That's why I love Newton, though, because it's so simple,
Yeah, but with these guys, Hamilton and Lagrange, and some of the work with that Noether, I always butcher her name.
I think it's Noether, whatever.
Noether. She with her bringing all that knowledge and coming in and converging on this thing, this idea, they started looking at systems or problems. You look at a physics problem. Now you're able to say, let me separate this from its sort of kinetic energy component. So meaning its motion.
The energy associated with motion of an object.
Yeah, exactly. It's sort of linear motion, as some physicists like to call it.
Kinetic energy can also be angular motion too, right?
Oh, yeah, sorry. Yeah. So you do have its like kinetic energy motion plus its potential.
Yeah, so all of its motion is encapsulated within the kinetic term.
Within these two things, the kinetic energy and the potential energy.
Yep.
And what physicists started to realize was, well, the kinetic energy doesn't really change. It's always going to look like a certain way.
Right.
1/2 mv squared.
Yeah.
Is what they'll get to. And you can watch your video about energy to kind of go through the history of how they realized that.
Right. That took a fucking long ass time.
That took a while. That took a while to get.
So you be thankful. You could take that for granted now, people who are doing undergraduate physics.
But nonetheless, the real cake, or the real sort of insight, was potential. The potential energy was the thing that was dynamic.
Right.
Meaning you that's the only thing you really change, and that's what changes your physics.
Right. So when you can find the potential, I mean, you're gold.
Yeah, then you just do some calculus, wham bam, you get to your answer.
Right.
Yeah.
And for those of you who are like, what the fuck are they talking about with potential energy? Potential energy is the other form of energy that basically it requires some type of force. So your system needs to be in some kind of force field. It needs to have force associated with it. Something that has force in the system is going to give it a potential energy.
Yeah.
So an example of that would be like if we're in a gravitational field, which we are, because Earth has gravity, the force of gravity is always pulling down on us. So if we're doing some problems with gravity being relevant, then that means you're going to have a gravitational potential energy. So anything that has a force.
Yeah. So yeah, and so pretty much anything that has a force is going to have a potential associated with it.
Yes.
And that's going to change on the context of your problem. So a lot of these guys were using this newly developed mathematical tools to figure out certain things. And it took a very long time to refine it and go through iterations to get to where we are now, but you'll run into a lot of that stuff. You'll see that a lot in theoretical dynamics, and we still use it in quantum mechanics, actually.
Yes. The Hamiltonian is the one that's used in quantum mechanics.
Yeah.
The one that's used a lot of times in classical mechanics or Newtonian mechanics, as we discussed earlier, is the Lagrangian.
Yes.
And of course, the Lagrangian's a little bit weird. I know a lot of people have had this question.
We've had this question.
What?
I think I know what you're going to ask, but go ahead.
No, I wasn't going to say anything about action. Not yet. I'm still reluctant to talk about it. We could, since we mentioned it though. I'll
mention it, but go ahead. Say your question.
I was just going to say that the Lagrangian is actually the kinetic minus the potential. And then you always wonder, why not kinetic plus potential? But the thing is, Lagrangian is different than total energy.
Yes.
Lagrangian actually has to do with minimizing the energy.
Yes.
So if you think about it, a kinetic minus potential gives you some number. It's the difference between the two energies. So you're trying to find the smallest number.
Yeah.
So it's not the same as total energy. It's different.
Yeah.
It's minimizing energy.
Yeah. The Lagrange is based off of basically the physics of things tend to take the path of least resistance, or the
path of least action,
which is what
they call
physicists like to say.
Yeah.
That's a more formal way of putting it, but in an intuitive sense, it's the path of least resistance, the path of
okay,
that the most energy efficient path is probably the one that nature is going to take. It's sort of Occam's razor.
Well, it is the one that nature is going to take.
That's the axiom, right?
Yeah.
But this is what it's going to do.
Right.
Mathematically, yes. So, yeah.
So basically, you're lazy because nature wants you to be.
Yeah.
So it's not your fault. That's all you got to know. Say the principle of least action requires you to be lazy.
So if your mom says, "Why haven't you cleaned your room?" just say, "Mom, I'm obeying the laws of physics." Okay.
Exactly.
Yeah. And yeah, man, it's just, so there's a clear, so we developed, like Terence is saying, that's why you developed the Lagrangian method and the Hamiltonian method, the total energy method and the difference in energy method. These are two different ways to tackle a problem in a sense.
Right. And they both actually have other parts of it that have some nuance to it as well. When we use the Hamiltonian, it has one of the parameters typically as the momentum and the position. Or the momentum and the position are usually parameters within a Hamiltonian.
Exactly.
And that's why we use it in quantum mechanics, because if some of you have heard of Heisenberg's uncertainty principle, you cannot measure the momentum and the position of a particle at the same time.
Exactly.
So we like to treat those two quantities separate
in the Hamiltonian formulation.
Exactly,
and the Lagrangian is less useful in that respect because it doesn't have momentum and position separated.
Yeah, like the way the Hamiltonian mechanics does.
Right.
Yeah, and that's exactly right, and that's something that you will not get until you have some wisdom in all this.
You might even be listening to this not right now, just like, what the fuck, if you're really beginning in physics. I mean, I didn't really internalize what that meant until a while after. I think probably even grad school. I mean, I knew that the Hamiltonian had to do something with that, but I just was like, I don't fucking get this. I'm just going to stick to the math, and we're just going to go. We're just going to shut up and calculate.
Yeah, but no, you realize that there's reasons that, because there's a constant philosophy in departments nowadays, there's just shut up and calculate. But when you appreciate the understanding of why we do things, I think you start to really be like, makes total sense. Yeah.
But of course, if you do shut up and calculate long enough, you might get some insights. So
either
way, you'll be fine.
Either way, you'll be fine. But in any case, we ended up with these two, and these helped us a lot. So, like you were saying, we use in classical mechanics is what they call, which is sort of Newtonian mechanics, which is sort of looking at how objects behave and the motion of basically objects.
Yep.
And like, you can be big or whatever, or in our regime, and then Hamilton. We can use Hamilton's equations and stuff to figure out problems also in our regime, but also in the quantum regime, which is
cool. You can use Hamiltonians in normal Newtonian scale as well,
and quantum mechanics, which is cool.
Yeah,
props to him.
You can actually do Lagrangian too, I think, in quantum mechanics, and I think there's there's the Feynman path integral formulation. I think uses Lagrangian.
Yeah,
that I have no idea what that is though. I suspect it has something to do with QFT. But I don't know anything about the Feynman path integral, so I can't really talk on it.
But I think it's based off the same principle of least action, minimizing action.
But I imagine that's venturing into QFT territory.
Probably.
Okay, so, you didn't do any of that in
we did, but
anybody?
We did.
Okay, but you didn't internalize it well enough yet.
No, I wouldn't say. But, but I wanted to move on to E&M.
Okay.
Because E&M, if you've noticed, is probably the only other thing the big thing that we haven't talked about.
Yeah. Fucking E&M.
Cursed
It's
E&M.
so cool, but at the same time, I find it to be one of the harder areas of physics.
Yeah, E&M
honestly.
E&M is colloquially termed from electricity and magnetism.
Yeah.
So magnets, what do they do? Right? Or how?
Now you're just trolling Juan.
Yeah. How do they work?
There you go.
Magnets. How do they work? What do they do? It's a little bit. It's a funny story, actually. The story of electricity and magnetism. When I say we, I mean the scientific community. There was a lot of guys that worked at developing the mathematics so that it was as easy as it is in modern representation of the Maxwell's equations today. They didn't look like that.
Right. It looked
horrible.
I mean, it was all over the place for a while.
It was horrendous.
Right? Yeah.
If you look back at the old manuscripts and stuff, it did not look like how it looks like today.
Yeah.
They cleaned up a lot of things. They refined the mathematics, and they were still using calculus, but they were learning how to use calculus and stuff, and tricks and dot products and stuff. And
this actually kind of goes back into our what we were mentioning in the beginning, was the beauty of mathematics.
Yeah.
So
that's what I'm saying. But this is why I have a point of contention, because because it just depends on how we represent the mathematics.
And that's what I'm saying, though. So maybe we're saying the same thing, but just in different ways.
Okay.
So to recap on the old video, Juan was saying that the math does not have to be beautiful, because nature is what it is, essentially. Is that correct,
Yes.
Juan? And then I said, no, it doesn't. That's not true, because math needs to be beautiful, or else you're not understanding the big picture. You're not understanding what's actually happening.
Gotcha.
So maybe we are saying the same thing. So when I'm saying the math needs to be beautiful, it's saying that your work ain't done yet. Until you've arrived at something like a Maxwell's equation version of what you've done.
Yeah.
That means you still got you still got cleaning up to do. It means you don't understand the system well enough.
But that's okay. So you're ascribing a condition that nature must meet to be true. That's my problem with this. That's kind of sentiment or that.
So maybe it's like an inverted logic, or maybe it's like an inverted way of saying it. like maybe I shouldn't say that nature is requiring math to be beautiful.
Yes.
Maybe the best way to say it is that nature works in patterns.
I would say there's a correlation, not a causation. I would say that's my problem.
Well, nature does work in patterns. I can.
No, yeah. No, I agree.
Yeah, because like everything we do is consistent. Well, there's consistency that we measure with physics and mathematics. Mm-hmm. So nature, as an axiom, I'm going to say works in patterns. Mm-hmm. Therefore, the mathematics that we ascribe to those patterns should be simple enough to where we can convey them in a way that humans can interpret, which I guess you could call, in some sense, beautiful. Mm-hmm. Because if the pattern makes sense and it's understandable at some level, mm-hmm. It's going to have some beauty to it. I don't think that nature's ever going to be so complicated that humans can't understand it. Well,
I think it can be.
Okay.
That's my problem. My problem is like you prescribe a condition for aesthetics for nature when necessarily it's, scientifically speaking, this is a feedback loop. Like us trying to refine our ideas, our mathematical ideas, and say, let's see if this works. Boom. Okay, it doesn't work. Okay, let's go back to the drawing board. And we keep refining this until we reach a representation that looks aesthetically pleasing. So,
okay, so you're saying we're forcing the beauty.
We're forcing is kind of a strong word. I would say it's more like, pardon me for using like so much, but by the way, pardon me for using like so much.
Oh yeah, you got to stop that because just a note, because when I do I transcribe audio for clips on Twitter, and like the fucking things. I also do this. I say a fuck ton. I have to delete so much. For you have to delete like a lot.
I'm sorry. I'll take speech classes next semester.
This is our practice time though. We're practicing our fluidity.
Yes.
We're failing, but we're going to try. At some point, we'll get decent.
So my point was that nature, we're ascribing an aesthetic principle to nature when nature doesn't necessarily need to be aesthetic. It's just what it is.
Okay, that's
true.
And
mathematics is a representation. It's not necessarily, it's a symbolic thing, and it may look aesthetically pleasing, but aesthetics is a human,
construction.
It's a human's construction, yeah.
So I think aesthetics is something deeper than human construction, though.
Okay, now you're getting somewhere.
It's like metaphysical, right?
Yeah.
I think it is, though, because I think nature has some kind of beauty, because I think patterns, for some reason, humans believe patterns to be beautiful, right?
Yes.
Why do we like patterns? I think
we like symmetry. We like, yeah.
And I think that's because nature is symmetrical. Nature has pattern. Mm-hmm. So I think there is some weird inbuilt thing where humans like symmetry because nature is symmetric in some fashion. So I think that the symmetry and the beauty of nature, how it unfolds, precedes the fact that we want it to be beautiful.
So it's a reinforcement loop.
Yeah,
it's a reinforcement loop in a sense. It's like it's a feedback of this is like this aesthetically pleasing? No, but nature tends to be follow certain things that are pleasing.
Yeah.
In a sense, symmetry or principles that we look for in a sense.
Yeah. So so it needs to be beautiful because nature is symmetric and beautiful. So I don't know if we would even have the concept of beauty in that sense if that wasn't already how nature operated. You see what I mean?
Gotcha, yeah.
Of course, this is like a metaphysical, like philosophy kind of thing where I don't really know for sure, but my suspicion is that. I'll say.
I will say it's a human inclination.
Yeah.
But that's all I can say.
I would imagine if we found an alien species that have never interacted, with us or anything, I think they would come to the same. They would have very
different representations,
similar,
but similar rules.
Yeah, I think they would have very similar constructions because it seems to be that nature has a consistency in physics throughout the universe. So
but
I would imagine
it's how you represent it.
Yeah, so I would imagine then that consistency, that symmetry, that beautification, simplicity is going to reflect in other independently, what would you call it? Independently,
cultures and whatever.
Independent societies and other planets, if they in fact exist. Yeah.
Yes. Okay. Well. Yeah, agree to disagree. I'm just kidding. I'm kidding. No.
That's always a good way to end a debate, right? Agree to disagree. If you're just like, fuck it, I can't argue anymore. Oh shit, well, I'm broke.
It's all right. No,
what is it?
My headphones fell.
Oh, okay.
So yeah, it's okay. So anyway, this
we gotta get back on track.
This idea. No, we got into this argument because Maxwell's equations.
Yeah.
The mathematics looked ugly until we reached, the beautification of Maxwell's equations.
Yeah.
And yeah, I mean, it took a while to get to that point. Maxwell discovered, or he put together these equations at the end of the last century, I think, late 1800s, I believe.
I can't remember the time,
yeah,
but I think you're right.
Yeah.
I'm pretty sure he's like a 1700s guy.
Yeah. You put them together in the late 1800s and people were like, wow, we finally discovered. And that's pretty much really that was kind of, you put a bow on electricity and magnetism.
That's why people say electricity and magnetism is like a completed part of physics.
Yeah.
It's a very beautiful and just like,
yeah,
bellissima.
Yeah,
like it's just,
Chef's
it's
kiss.
so wrapped up, and it's just really nice and wrapped up.
Yeah, there are things that you can apply to the extreme, like quantum electrodynamics was something that was developed, but it's kind of a limit to that.
Yeah.
But in essence, we were like, wow, we can solve a lot of problems with these simple equations.
Yeah,
these
the Maxwell's equations.
Postulates. Yeah.
Yeah, and if you see Maxwell's equations, that's the one that uses like the del operator a lot, which is the Greek nabla. It's like an upside down triangle. I'll put it in the video.
You see upside down pyramids and crosses and dots and
integrals.
So
they've really like you can think of it in terms of like ham-fisted the niceness in some ways. Because,
that's what I'm saying.
Yeah, because nabla is like this abusive notation according to Wikipedia, because we treat it like this vector quantity, right?
Yes.
But it's like a vector of differential operators, which is like, what the fuck does that mean?
100% agree with you, man.
So it just looks really nice, and it's been simplified to a point where we made it make sense.
We made it look nice.
That's true. That's
what I'm saying.
But I guess we could write it also as like divergence and curl.
Uh-huh.
You know how like in certain textbooks they actually write out like div for divergence and then curl curl.
Yes.
So you could do that. I guess it wouldn't look as beautiful as the nabla.
But this is what I'm saying. These are all, by the way, these are like divergence and curl and stuff. These are all grad.
Yeah,
gradient.
And Laplacian, of course.
Yeah, these are all calculus. These are all embedded in the representation of calculus.
Yeah,
by the way,
those you'll learn in vector calculus.
Those you'll learn in calculus 3. If you go to university, you'll typically see them there. So yeah, so that's kind of the point of. I think that's. Oh no, we didn't even get to Schrodinger.
Oh, let's do it. We're sitting at 57 minutes. Let's get to
good.
It. Yeah, let's get to it.
Okay, let's just put a bow on it, because this is so. I mean, we're leaving out statistical mechanics on purpose, by the way.
That one's hardest.
No, it's not hard. It's just
we always
simple.
leave out statistical.
But it's always so simple.
It's not, though, because the partition function is really fruitful.
But the math is necessary. It's not that difficult, though.
But the partition function, dude, is kind of cool. And then there's the distribution functions as well.
All right. So maybe we can spend a whole episode on StatMech. Because we talked about quantum.
Maybe we owe it to StatMech.
We owe it to
because nobody ever talks about StatMech. Everybody wants to sweep it under the rug, and that's our field.
It's the ugly stepchild of physics. Where you just got to throw it in the corner.
But we're condensed matter physicists, so we should care about StatMech way more than other people do. We need to give it.
Yes.
We need to serve it justice. Let's commit to that. Let's do a whole video on StatMech at some point.
Okay.
Right?
And I will say that the reason why is because a lot of physicists think of statistical mechanics or thermodynamics as an engineering problem, as like an engineering study. It's like, oh yeah, whatever.
It's got its foot definitely in the engineering corner, because and that's why I like it though. It's got so much. It's got so much like practicality to it.
Yeah, you can build a lot of intuition with a good understanding of statistical mechanics.
Right.
So yeah.
Anyway,
but going on to Schrodinger's equation. This now we're in the sort of, we're in the now almost 2020 here in this on this timeline. But we're gonna rewind backwards to 100 years, and we end up at quantum mechanics, the foundation of quantum mechanics, and we're still using calculus.
Yep. This
is the realm of Schrodinger. This is where Schrodinger comes in.
Right.
And he says, he's like, okay, I like the idea of total energy. We're still going to keep that, right? Because he was sort of modeling, the theoretical model for Schrodinger's equation was based off of a few experiments, which are the Young's double slit experiment, where it looked at particles as a wave.
Well, both.
Both.
They would. It would be a single particle would go through two slits at one time, which is freaky physics. They're like, how can a particle go through two slits at once?
Yeah.
And then you produce an interference pattern, which was like a wave property. Mm-hmm. And then if you observe the particle, if you measure the particle, I should say, it would only go through one slit, which gives you the classical notion.
Yeah. Principally speaking, they were like, well, the mathematics shouldn't necessarily change, but then, they came to certain experimental conditions came out so that it put limits on what you could figure out, Heisenberg's uncertainty principle.
Right.
And like you were saying, the Hamiltonian representation was more favorable.
Yeah.
So
because you couldn't measure momentum and position with absolute precision at the same time.
Yeah.
You got to pick one or the other.
Yeah. So
or you measure kind of both of them in a fuzzier way.
Yeah. So naturally, they're like, okay, let's move on with using Hamilton's total energy picture or regime or formalism. And if you look at any modern sort of textbook or whatever, you'll see that they use the first derivative
for time.
Yeah.
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 Yeah. That's the whole purpose of one of the biggest purposes of Schrodinger equation.
I had a question about this for a professor, because I was like, why wouldn't you? I was like, I don't know. I'm going to cut this out.
No, you don't have to cut it out. I can maybe expand what you're saying.
No, it's because I'm like lost. Thinking about.
Well, maybe you can think about it and I'll talk a little bit.
Okay.
So I know the thing is, the Schrodinger equation, the big insight was, okay, particles are waves and particles at the same time, right?
Yeah.
Okay, so that means that if we get down small enough, the wave properties start to actually matter. So that means that their Hamiltonian needs to be given by some wave function or some wave equation. So then, of course, we already knew about the standard wave equation, which is basically a second order differential equation
from optics.
Right, where you have some second derivative with respect to position and some second derivative with respect to time. So then Schrodinger equation was like, but fuck this double derivative with time. I don't remember why. I think it couldn't be solved with the double derivative of time. Well, this is why I was thinking
about the second derivative of time, because I was like, oh, it's a wave equation.
Yeah,
thing.
It is.
So I did. My bad. Yes.
The thing is, Schrodinger kind of came up with this equation. There's no real derivation of the Schrodinger equation.
Right. It was formulated from experimental.
Right. He said it should look something like this. So fuck it. Let's see if it's right. It's right.
What physicists like to call it an ansatz.
An ansatz. Okay.
Ansatz.
Yeah. Like you get
educated guess.
Yeah. You kind of guess the solution.
Yeah.
Feynman says this. If you can guess the solution, then why not? Right. So he knows it should be something like this to work. So he goes to the math and uses some kind of axiomatic, ideals in his mind, where he knows it's got to have the X, Y, and Z. But he does this and goes to the math and finds out the Schrodinger equation needs to look like this. It's a second order differential equation with respect to position equal to a first order differential with time. And it turns out that actually was the correct equation, and he was able to use that to predict the wave nature of single particles.
Yeah.
Or I guess not even single particles, more than single particles too.
Yeah.
So did you have time to think about what you were saying?
Yeah, I kind of went off on a tangent.
Okay.
But no, you nailed it. I mean, you nailed it. That's exactly what it is. And yeah, it's, I mean, that also has limitations. So that equation also reached limitations because in most practical applications, you don't necessarily have, I mean, yeah, you have your potential, meaning you have a force acting on something or a particle or something. So you can get a total energy picture, and then you take your data and then take a derivative, and you should get a solution that looks like so-and-so, right?
Right.
The issue here is that there was a more favorable representation, and that was by Heisenberg representation, which is most commonly known as like maybe matrix mechanics is what they like to call it.
Oh, okay.
So the matrix representation of quantum mechanics, I think in modern textbooks has won out.
Oh, really?
Because of Dirac, because you fast forward a couple years and Dirac notation now becomes way more useful.
Yeah, yeah.
But Dirac's notation is based off of matrices.
Yeah.
So the matrix mechanics comes in, and matrix mechanics is literally just linear algebra.
Right.
Just linear algebra with some axiomatic things that we apply beforehand with the physics rules. And yeah, it I mean, I don't know what else there is to say, just the fact that, you know, linear algebra was developed much long before, right? This was I wouldn't say linear algebra was developed to push quantum mechanics. In fact,
no, I don't think so.
In fact, I think linear algebra was developed way before.
I think probably because it makes sense.
Oh yeah, because algebra, algebra and the
doesn't mean
system of equations.
But the thing is that representation and all that may not have been developed.
I gotcha.
You know, it doesn't
necessarily follow.
Gotcha.
My hunch is kind of clever. It has some clever tricks to it, for sure.
My hunch is that it was developed much earlier than quantum mechanics.
Okay.
That's my hunch.
I'm pretty sure it was not intended for quantum mechanics, though. It just so happened to use the same mathematics.
Yeah.
Yeah.
So, yes. So Heisenberg came in and basically abandoned or just said, nah, the Schrödinger equation is cool, but, you know, guess what I can do? I can look at many particle systems, or I can look at different, you know, an infinite number of states. Boom, 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 boom. Put them in an infinite space.
Right. The Hilbert space, as they call it.
Yeah.
Now we're getting abstract fucking Candyland
so
over
now
here.
Physicists are like, yeah, let's put our theoretical hats on.
Yeah. And this one bugged me for a long time because I couldn't find a way to like internalize it.
Yeah.
But then that's when I learned. At some point, I learned just stop fucking trying to understand quantum mechanics and just understand the math.
No, that's all you can do. I mean, you take no. It's like, how about it? Physicists like this, like you. It's like you learn all the ingredients, then you cook it, right?
Okay.
And when you cook it, you're like, okay, I'm not sure if this is going to come out good. You know, you put all your ingredients together and you're cooking it. You're like, maybe I'm like doing this wrong. And then you eat it, and if it tastes good, then you know you're like, okay, this works.
That's actually a really good analogy.
And then you but then. You know, you still have to digest it. So when you digest it, you know, it might not make a lot of sense to your stomach sometimes.
Right.
Sometimes it'll come out real nasty.
You know, that's why I actually like physics too, because we actually get to test our fucking cookie. And mathematics, sometimes you can't test your goddamn cookie. You know, I guess there's probably ways, but in physics it's so much easier a lot of times, right? Because you know that if it ain't squaring away with reality, like you know, you take certain limits and then you see if it doesn't collapse into a classical version of your equation,
right?
It's wrong, right?
Yeah.
So it's like you have a lot of checks and balances for sanity, and then you also have your units too. Like your units, if your units don't match, then something's off.
Doing something wrong. Yeah.
Yeah. So the amount of times I've been saved by just checking units on something like is like
powerful units. But anyway, circling back to I mean, a lot of this stuff doesn't make sense until you digest it and really think about it. And it can sometimes be hours, or not even hours. I mean, if you look into memory and learning, what you'll often find is that people, like, they've done studies on this, and when you learn something, you feel like you have not learned it well enough, but they'll come back to the same people that learned this topic in 2 weeks, and they've actually retained a lot more information than they thought they did.
Yeah.
Which means that, like, learning things, it's not necessarily it doesn't happen in an instant.
Yeah.
It takes time for your mind to actually digest these concepts and stuff.
Oh, 100%.
Yeah.
And you really feel this in physics, because I feel like, when I'm in the semester, I'm just like, I don't know shit. I didn't learn anything. Like, I did a bunch of stuff, but I didn't learn anything. Then once you're out and you actually have time to process all this stuff, I feel like I've like mulled over so many things that I actually am starting to understand.
Yeah.
It's always afterward. Once you see that, okay, I'm done, I can finally just
sit down,
go through and think of these things. You learn a lot of shit after the fact.
You realize that your mind is constantly refining the thoughts and stuff.
And connecting the dots all the time.
Yeah. It's totally true. So don't feel like inadequate if you're in our situation where you're learning something, you feel like you haven't taken anything from it. This takes time. This, like, we have this bird's eye view now because we've been in it, right?
Yeah.
So and I hope that this makes sense, like, as far as like how these people have formulated the physics, the mathematics that's required of physics in a sense. But yeah, I mean, I don't know. I guess putting a bow on, like, I feel like that's where we kind of can stop, because linear algebra with Heisenberg's formulation, like, I think we kind of did a topic on this already for quantum mechanics. So you can look at that video.
They can go back and look at the quantum mechanics.
Yeah, because we go into like Hilbert space stuff and what all that means.
We don't get too heavy on the math. No. We're still, of course, mostly talking about it, because you can't really do math on a podcast, right?
No, you need a drawing board for that.
So we keep it still in the philosophy of physics territory, but it's still interesting. Yeah. So check it out.
So yeah, I mean, what would you say? Is there anything else you think that we can?
I think that's probably good, man. We're sitting at 71 minutes. Do you have anything else?
I mean, you said, I guess, to top it off, the last thing.
Yeah.
Can you do physics without math?
Oh. No, I don't think you can. I think you can I don't think you can, because math is like, it's the only way to hold all of these really deep concepts in your brain in a simplified way. Mm-hmm. Like, I think you could do maybe basic physics without math, but it's making it harder for you, because the use of symbols makes things so much easier for your brain to digest.
Yeah.
You know how when you have your brain, they say your brain can only hold 7 to 9 concepts at one time in your short-term memory. Symbols allow you to do that, because you're only thinking of one symbol to represent some giant concept. And the more you stack up concepts on that, you get these really, really huge chunking effects. Chunking is this phenomenon where you can take in, like, let's say if you take in words at a time, you can take in a lot of words at one time. Like, let's say you see like the word school bus, you see the word Rubik's, and then you see the word computer. I'm just looking at objects in Juan's room except for the school bus. But if you take those 3 words, you've now effectively chunked all those letters together, and that's one concept in your brain at one time. Yeah. So that's kind of what symbolic language does, or math does in your brain for physics. Yeah. So I don't think you can really do it that easily without math. What do you think?
No, I agree with you, actually. This is, I mean, it's not surprising, right? Because you're if you've ever had somebody explain a problem to you, and or even had told a story to you that doesn't have a clear enough narrative, sometimes you feel like there's a lot of building up.
Yeah.
You're like, where's the story going? And especially if it's visual, you can kind of be like, wait, so this happened and then this happened. You have to kind of draw a mental image, and the physics have this happen to you. Have somebody, write a sort of, or read a physics problem to you, that you might understand.
Yeah.
In clear English words, and it won't make sense.
Yeah, it's too much to hold in your brain.
Too much to hold in your brain. It really is. You need the symbolism, like Terence is saying, to really help you get to the crux of the problem and or help you solve the problem. I had this issue the other day when I was trying to explain a problem that I was having with this problem that I was dealing with, and I told my friend, I was like, man, if I do the calculus this way, it doesn't make sense. And he was like, but you did this. And I was like, yeah, I did that. He's like, well, you should do this and do the calculus this way. Mm-hmm. And I was like, I did. And then, so we were kind of like in a loop, and I was like, I need pen and paper. I need to show symbolically what's going on.
I hate talking with people about math unless they're being really like clear about things. I've noticed that I don't like talking with math to a lot of people because of that. Like, they'll say, oh, you just do this with the Hamiltonian and you do this, and that. And I'm just like, this doesn't really help me. I don't know what you're saying.
Yeah. Professors are guilty of this.
Yeah. Like you gotta like either tell it to me in a conceptual framework, or you gotta have really, really well laid out math of what you're saying.
Yeah. And a lot of early on in physics, like the Greek guys, that's how they did physics. They just talked about it a lot of the time. Yeah. But what would have put them a step above everyone else would have been to find ways to symbolically represent these things.
Right. Right. And this is why we don't really talk about math in a podcast and saying like, take the derivative of X, Y, and Z,
Yeah.
Because it doesn't really translate that easily. Conceptual is much more fruitful in a conversation.
Yes, 100%. And if you've ever seen if you guys are fans of, physics podcasts, or if you've seen TV shows, you
like The Portal or Mindscape.
Yeah. You tend, I feel like, even my own eyes tend to gloss over whenever they start talking about math. And I sometimes critique them. I'm like, why would you take it there? I mean, you can explain certain low-level topics that are already kind of easy to intuit. Mm-hmm. You can talk about that, but when you talk about higher-level stuff, it's just, you need too much layers. Of a foundation. Yeah, there's too much to build on that is not accessible to a lot of people. Yeah. And the nuance will be lost. And some people might say that, well, you're not giving the general populace enough credit, but
I think it's a brain wiring issue. It's just
this is the way humans' brains are wired. We can't. Maybe there's some genius out there who's a mathematical,
and he's like, that makes sense. No,
but most people, this
is why people like Joe. This is people like Joe Rogan, right? Every time he has somebody on, he's like, my brain hurts, and where he's talking like that.
And I get it, because as soon as they're talking like that, I'm like, I already know why he is, because he's stuck on the fundamental principles of math. Like when Eric Weinstein talks to Joe about derivatives and stuff, like derivative is already a game changing concept. Like, if that's your basic starting point, then it's already out the window, basically.
100%.
But I think Eric's also talking for the audience at large, like he says, so he doesn't like to dumb things down. And I like his. I think that's a noble methodology.
Respectable.
Yeah,
I respect it.
It's just he's doing a different thing than I would do.
Yeah.
If I was sitting in front of Joe, I would try to convey it to Joe. And I also try to pull in laymen, because I like to give people, my philosophy is I like to give people morsels. Because when they have the morsel, they take that in. Mm-hmm. But Eric likes to give you the badass picture first, which is still kind of a morsel. It's just like a giant cookie that you cannot eat it at all.
Yeah, 2,500,000 calorie cookie.
I like to give people a little cookie here and there, and then they can take that bite.
Are you ready for the next one? Open your mouth. Here it comes.
So but I like his methodology too.
Yeah.
But anyway, we're rambling. So I guess let's finish off with a question here, Juan. You got a question at all, man?
Man, I kind of don't, actually.
Okay, I got one. Yeah.
Okay, yeah.
I'm saying I think we should, since the debate on the beautification of math was kind of an interesting one to people last time, let's see what everybody else thinks. What do you guys think? Does math need to be beautiful to be correct or not? What do you think?
Yeah.
And with that, I guess we will see you in the outro.
Yeah.
See you guys. You did it, guys.
You did it again. Thank you for making it this far. Don't forget to leave a like, answer the question in question, and share, right?
Share, subscribe.
Subscribe. Did I say comment? Yeah, I said comment. And yeah, just thank you for being fans.
Yeah, guys,
and keep on keeping on. So we will see you next episode.
Yeah.
All right, bye, guys.
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 Yeah.